Hey Chem Kids, Campbell here. In our first video on Chapter 18, Acids and Bases, we're going to talk about what are the properties of acids and bases, what are they, so what is their definition, and we're even going to talk about what a conjugate acid and conjugate base are. All right, let's look at some of the properties. So if we taste acids and bases, and remember, never taste anything in lab, acids taste sour. In fact, if you've ever had a Sour Punch straw or a Sour Patch Kid, you're actually eating something that's coated in acid. What? You can eat acids? Well, okay, some of them. Bases actually taste bitter. Soaps are bases, and if you've ever had your mouth washed out with soap, like me when I was a kid, you know they taste bitter. From a feel standpoint, acids, they just feel like water if they're weak. If they're strong, they burn. In fact, they start to itch first, and then they, ooh, ouch. Bases are actually slippery, right? If you have a bar of soap, it's slippery. Bases are actually slippery, and if they're strong, they will burn you as well. Now, there are these indicators, and here's litmus paper. I have red and blue litmus paper. If I have an acid, it'll turn litmus paper red. And if I have a base, it turns the paper blue. Now, just to show you this, here's a piece of red and blue, and if I put it on my tongue and measure the pH of my saliva, you'll see that it really didn't change the color. Red's still red, and blue's still blue, which is good because my saliva should be neutral. But now, I stuck on the Sour Punch straw. So sour. And I put the litmus paper back in my mouth. You can see red's still red, but now my blue one is red as well. Acid! Yikes! Not all acids are bad. In fact, vinegar is an acid as well. That's acetic acid. So what are some other common acids and bases? Well, if you drink soda, you're drinking carbonic acid. Or lemonade, or lemon juice, is citric acid. In fact, that's usually what's on the sour candies. If you've ever cleaned a toilet, that's hydrochloric acid. And then some bases. If you've ever cleaned windows, Windex uses ammonium hydroxide, which is a base. And soap, like I said before, is also a base. So what is an acid and base? Well, back in 1887, a Swedish chemist, Arrhenius, came up with the definition that said that an acid was a substance that dissociates or breaks apart in water to produce hydrogen ions. So if I have hydrochloric acid and I put it in water, I get hydrogen ions and I get chloride ions. And he said a base is a substance that breaks apart in water, that dissociates in water, and produces hydroxide ions or OH ions. So there's my sodium hydroxide, and we put it in water and we get sodium ions and we get hydroxide ions. And so if we look at some common acids and bases, we can see that all of our acids, right, all acids always have hydrogen, right? They always start with H when we're doing nomenclature. And here are some common bases. So this definition is great for a lot of acids and bases. The problem is, well, it doesn't always work. In fact, one, it says that we always have to have water. So that's a problem. It also is really oversimplifying what's happening to the acid when it dissolves in water. But the biggest thing is, too, that it restricts all bases to having hydroxide ions. So they all have to have OH. And we know that not all bases have hydroxide. NH3, ammonia, is actually a base, but it doesn't have OH. So there was some stuff that's wrong with Arrhenius, but it wasn't until about 1923 when two other chemists, Bronsted, who was Danish, and Lowry, who was English, came up with a more appropriate definition. And what they said was an acid is any substance that can donate hydrogen ions, so it can give them away. And a base is any substance that can accept hydrogen ions. And this is the definition that we use today. Now, one of the things about their definition is that it solely focuses on what's going on with the hydrogen ion. So it doesn't restrict bases because all bases have to be is something that will take a hydrogen ion. Now, if you think about what a hydrogen ion is, a hydrogen ion, right, hydrogen only has one electron and one proton. And so if we remove the electron and make it an ion, what do we got? We just got a proton. So a hydrogen atom is actually just a proton. Pretty cool. If we look at an example of a Bronsted-Lowry acid-base reaction, I have here hydrochloric acid plus water. So now it's not dissociating in water, it's actually reacting with the water. And if we look at the hydrochloric acid, here we can see hydrogen with the chlorine, but if we look at the product side, we see chlorine by itself. So what that means is hydrogen has donated its hydrogen atom, the hydrochloric acid has donated its hydrogen ion to the water, and we can see that because if we look in the product side at the water, water now has 3 hydrogen atoms to it, where it only had 2 before. So that makes hydrochloric acid here the hydrogen ion donor. It gives it away, it's donating it. And water is the hydrogen ion acceptor because it's accepting it. And according to Bronsted-Lowry's definition, that makes hydrochloric acid the acid, not just because it's in its name, because it's donating hydrogen ion. And water, in this case, is a base because it's accepting that hydrogen ion. Now, what's the deal with H3O+? H3O+ actually has a name. It's called a hydronium ion. And the thing is that hydrogen ions, these protons, don't exist by themselves in a water solution. What they'll do is they'll seek out water molecules, and they'll actually attach to the one side of the oxygen. And that makes H3O+. So you're going to see in this unit a lot of stuff about hydronium ions. That's just my extra H+. Let's take a look at another example. Here I have ammonia, NH3, reacting with water, and I get NH4 plus OH. Now, if we take a look at the NH compound on both sides, notice here it has 3 hydrogens, but in the products it has 4. That makes it the hydrogen ion what? Donor or acceptor? Did it donate it, give it away, or did it accept it? Well, if I gained hydrogen ions, that makes me the acceptor. And if I'm a hydrogen ion acceptor, am I an acid or a base? I'm a base. So in this case, my ammonia is the base and my water is the acid. Notice that over here, I'm missing a hydrogen. So the water actually gave it away. So what's up with water? In our first example, water was a base, right? It was the acceptor of the hydrogen ion. And I became H3O+. But in the second reaction, water was the donor, and it gave it away. It was the acid. Well, there's a name for that. That's called amphoteric. A substance that can be both an acid and a base is amphoteric. Here's another example. If we take the carbonate ion and we add a hydrogen, right, it can then either accept another one and become carbonic acid, and if it's an acceptor, right, then it's a base, or it could donate that hydrogen ion it has, and if it donates it, right, then it's an acid. So this is another example of an amphoteric substance. All right, let's talk about our last topic, conjugate acid and base pairs. Conjugate acid and base pairs are formed when a hydrogen ion is donated or accepted. So really what conjugate acid-base pairs occur in, they're the products. Our acids and bases are the reactants, and the conjugate acid or base are the products. So anytime a base accepts a hydrogen ion, it becomes a conjugate acid. So a base becomes a conjugate acid. And the reverse is true. When an acid loses that hydrogen ion, it becomes a conjugate base. So an acid becomes a conjugate base. So they like flip roles. Now, like I said, these are products. The acids and bases are the reactants, and the conjugate acids and bases are the products. Huh? Oh, you can't see the monkey. He's scratching his head. So let's take a look at a reaction. Here we have that hydrochloric acid reacting with water to produce the hydronium ion, H3O+, and chloride ion. Now, we said that hydrochloric acid was my acid, right, because it donates, it gives it away, because we see over here chlorine doesn't have it anymore. So if I have an acid, it becomes a conjugate base. So HCl is the acid because it donates the hydrogen ion. The chloride is the conjugate base because it's the pair to the hydrochloric acid. In this case, water, right, is the acceptor, so it's the base in this example. And on the other side, if I was a base, I become a conjugate acid. So the hydronium ion here, H3O+, is the conjugate acid. So it's what the base becomes when it takes in that hydrogen ion. And the chlorine is the conjugate base. It's what the acid became. after it donated the hydrogen ion. So what I want you to look for is figure out who the acid and base are, and then find them on the other side of the reaction, and they're now the conjugate of the opposite. So the conjugate acid comes from the base, and the conjugate base comes from the acid. They flip roles. So let's take a look at this reaction. I have ammonia reacting with water. That's our second reaction. We get NH4 plus OH. Now remember, we said that NH3 was the base because it's the acceptor, right? We have one more hydrogen ion over here now with the nitrogen. So if this is the base, what do we call this? The conjugate acid. And here's my acid. So we find it on the other side, and we call it the conjugate base. And we call these conjugate pairs. So the NH3, NH4, those are pairs, right? They go together. And water and the OH ion, those are my conjugate pair. And acid becomes conjugate base. All right, now you figure this out. Here we go. I want you to pause the video and see if you can figure out from this reaction which is the acid, which is the base, and then identify the conjugate acid and the conjugate base. Did you get it right? So if you said that HCN was the acid because over here it doesn't have the hydrogen ion, right? It's a loser. The acids lose the hydrogen ion. So if you said this was the acid, you were right, which makes the CN now the conjugate base. And if you said that the SO4, our sulfate here, is a base because over here it accepts a hydrogen ion as one more, it's a gainer, then you were right that this is the base, which makes this the conjugate acid. All right, let's try another one. How about in this reaction? Pause the video, figure out the acid, the base, the conjugate acid, and conjugate base. Is this what you said? If you said that this, which is acetate, is the base because here it doesn't have the hydrogen ion, here it does, that makes this the base, right? It's the gainer, and that makes this side the conjugate acid. And you said that this was the acid because here it has two hydrogens and here it has one, it's a loser, then it's an acid, it's donating that hydrogen ion, that makes this the conjugate base. How'd you do? All right, we'll talk some more about this in class and do some more practice. So I'll see you in class.